Okay, moving on to our next topic, which is gradually varied flow. The derivation of gradually varied flow is very, very important, and it's a frequently asked previous year question. So, we have already discussed what is gradually varied flow in the module 4 itself. That is, if the depth of flow in a channel changes gradually over a long length of the channel, the flow is said to be gradually varied flow and is denoted by GVF. Okay, that is, if you're if there is an open channel and if the depth of flow is changing gradually, not rapidly. If it is changing rapidly, then it's a rapidly varying flow. And if there is no change in the depth of flow in an open channel, that is a uniform flow, isn't it? There was uniform flow, rapidly varying flow, and gradually varying flow, isn't it? So if there is no change in the depth of flow in an open channel while the fluid is flowing through the channel, then it is known as a uniform flow. And if the depth of flow is rapidly changing over a short length of channel, then it is a rapidly varying flow. And if the depth of flow is gradually varying over a long length of channel, then it is known as a gradually varying flow. Okay, now coming to the derivation of this gradually varying flow, there are a set of assumptions which is very, very important. You have to write this down if they are asking the derivation for the gradually varied flow. That is, our first assumption is the bed slope of the channel is small. That is, we are taking the slope to be very small. That is, in this diagram itself, this is the bed slope IB. You can see that the slope is very small, isn't it? So we are assuming that the bed slope of the channel is very small and flow is steady, and hence discharge Q is constant. So we are taking a steady flow. Okay, that is, there is no change in the flow properties with respect to the time, and the discharge Q is constant. There is a constant discharge. Discharge is not varying. And our third assumption is the accelerator effect is negligible, and hence hydrostatic pressure distribution prevails over channel cross section. We are not taking any accelerator effect. For that resultant force is actually we are equating it to zero. That's what they have meant. Okay, we are not taking any accelerator effect into action. And our next assumption is the energy correction factor. We know this, right? Alpha kinetic energy correction factor. We are taking it as unity. And the roughness quotient, our next assumption is that the roughness quotient is constant for the length of the channel and it does not depend on the depth of flow. Roughness quotient is constant and it's not depending upon the depth of flow. And next assumption is the formulas such as the Chassis formula, Manning's formula, which are applicable to the uniform flow are also applicable to the gradually varied flow for determining the slope of the energy line. We have already studied what the Chassis formula and the Manning's formula, etc., right, in the previous module. It was for uniform flow. We are assuming that these can also be applied for the gradually flow. Okay. And our last assumption is that the channel is prismatic. That is, it is not changing its cross section while it's flowing. Okay. Now, consider a rectangular channel having the gradually varying flow. The depth of flow is gradually decreasing in the direction of flow. Okay, it is varying, right? It have to increase or decrease. So, we are taking it as the depth of flow is gradually decreasing over the length of the flow. If, in the direction of the flow, we can see that this is the depth of flow. This much is the depth of flow. It is gradually decreasing. Okay. Over a long length of the channel, if the depth of flow is gradually decreasing, it is known as a gradually varied flow. Now, these are the terms. That Z is the height of the bottom of the channel above the datum. Now, we are taking a horizontal line as a datum, and the height of the height of bottom of the channel above datum is, we are taking it as Z. This much is Z. This is our channel bottom. This is the slope of the bed slope. Sorry, this is the slope of the channel, or slope of the, that is the bed slope of the channel, IB. And we know that this depth of flow is gradually decreasing over a long length of the channel. That this much is depth of flow, that is the height. Sorry, this H is the depth of the flow. And this is the free water surface. And parallel to this free water surface, we can see, we can plot the energy line, that is kinetic energy line, isn't it? So IE, that is the slope of the energy line. I am marking this as the slope of the energy line, that is IE. Okay, so this is the energy line. This is the slope of the energy line, IE. Now, we know the energy for the, equation for the total energy, which is E is equal to Z plus H plus V square by 2G. That is datum head plus potential head or pressure energy plus kinetic head, that is V square by 2G. So, what we are doing is for getting the expression for the gradually varied flow, we have to differentiate this energy equation with respect to x. Okay. Now, differentiating with respect to x, what will we get? We get dE by dx is equal to dz by dx plus dh by dx plus d by dx of v square by 2g. Now, we can write v in terms of q by a, right? What is v again? V is the mean velocity of the flow. Okay. Now, and q is the discharge to the channel. We can write v as q by a, isn't it? That is q is equal to AV, and q, we can also write it as q by b into h, that is area is width into depth of flow. Now, I am expressing v in terms of q by bh in this equation. Then we'll get an equation like this. That is dE by dx is equal to dz by dx plus dh by dx plus d by dx of q square by b square h square by 2g. How did this become q square by b square h square? Because that is b square here. That's why. Okay. Now, we can see that in that equation, the discharge and the width of flow and the G is a constant. That is, in this equation, this terms Q, B and G is a constant, isn't it? So, we can take this out. So, I am taking Q square by 2B square G outside and writing it like this. That is dE by dx is equal to dz by dx plus dh by dx plus q square by 2b square g into dy dx of 1 by h square. Now, when we differentiating this term, that is 1 by h square with respect to x, what will we get? We know that 1 by h square, the differentiation is, we can also write it like this, right? H raised to minus 2, that is x raised to n. What is the equation? Differentiation equation, nx raised to n minus 1. We'll get it as n. N is minus 2 here. Minus 2 into h raised to minus 3. So, I am writing it as minus 2 by h raised to 3, okay, into dh by dx, because we are differentiating this term with respect to x and there is no term of x here. So, into dh by, we have to do into dh by dx. So, we'll get an equation like this now, that is dx by dx, dz by dx plus dh by dx minus of, why it became like this? I have substituted the value of d by dx of 1 by h square here, that is minus 2 by h cube into dh by dx, and 2 and 2 got cut off and we got an equation like this. So, dz by dx plus dh by dx minus q square by b square h square, isn't it? 2 and 2 got cut off into 1 by g into h. How did this become h here? I am writing this as a different term because we know q by bh is v, right? So, in order to rewrite that, I am splitting h cube into h square and h, so into dh by dx. So, this term we know this is v, q by bh is v, isn't it? I have already expressed this. V is equal to q by bh. So, this is actually q square by b square h square is actually v square. So, we get something like dz by dx plus dh by dx minus of v square. This is v square into 1 by gh, right? That is minus v square by gh into dh by dx. Now, we can write this like this because we can take the common term outside. That is dh by dx is there. It is common in this term and this term also. So, we will get it as dE by dx is equal to dz by dx plus dh by dx into 1 minus v square by gh. Now, if we refer this figure, we can see that if I am taking this as the positive x direction, okay, and if we are going through the positive x direction, or if the x direction of the x term is increasing, we can see that that is the datum, that is height of the height of the bottom of channel above the datum, height of the bottom of the channel above the datum, it is decreasing. That is, this is my, sorry, This is my x direction. If I'm moving towards the positive x direction, we can see that the z is getting decreased, right? This is getting decreased. And we know that the slope of the channel bottom is IB, isn't it? It is IB. We can take this IB as negative. Why? Because while we are moving through this positive x direction, we can see that the z is getting decreased. That is, the height of the bottom of the channel above datum is getting decreased, and the slope of the channel bottom, I am taking IB as negative. And similarly, we can see that when I am moving in that positive x direction, the total energy, this total energy is this much, right? This much of total energy is also getting decreased. The energy line is also getting decreased. There is a decline, right? So we can take the slope of the energy line also as negative. Okay, so I'm expressing IB and IE as negative now, and dE by dx is nothing but the slope of the energy line, isn't it? That is, what we have done is we are differentiating the energy with respect to x, and dE by dx is actually the slope of the energy line, that is IE itself. So I can mark it as IE. But since I am moving in the positive x direction, that is, this is the direction of the flow, right? So along the direction of the flow, both IB and IE, we are taking it as negative. So dE by dx is nothing but the slope of the energy line, and which is expressed by IE, which is also expressed as minus IE, isn't it? This is actually minus IE because along the direction of the flow, the slope is getting decreased, it seems. So I'm taking it as minus IE. And what is dz by dx? This is actually the slope of the bed of the channel, isn't it? Slope of the bed of the channel. What is the slope of the bed of the channel? It is nothing but IB. This is also getting decreased along the positive x direction or along the flow. We can see that z is also getting decreased. So we are expressing IB also as negative. So dz by dx is IB, and I'm marking it as negative IB. Okay, because why? Because z is decreasing along the direction of flow, and also E is decreasing along the direction of flow. Plus dh by dx into 1 minus v square by gh. Now rewriting this, IB goes here, it becomes positive, right? So IB minus IE divided by, this term goes here, 1 minus v square by gh is equal to dh by dx. We get something like this. Now this, what is this v square by gh? We know v square by gh is, what is v square by gh? We know what is Fruit's number, right? Fruit's number is nothing but v by root of gh. Now if you get squaring this, that is fr square is equal to v square by gh, and we now know that v square by gh is nothing but fr square. So substituting fr square there, we'll get dh by dx, that is the slope of the free surface of water, as IB minus IE divided by 1 minus fr square, and this is the equation for the gradually varied flow. Okay, now we have obtained the equation for the gradually varied flow, and under this there are three cases. Okay, that is, if the dh by dx is equal to 0, that is the slope of the free water surface is 0, means the depth of flow is constant, that is the depth of water above the bottom of the channel is constant. So if it is so, then the free water surface is parallel to the bed of the channel, isn't it? Because depth of flow is constant means that it is not decreasing or increasing, right? It will be, if the channel bottom is like this, it will be parallel to that. There is no change in the depth of the flow. And if dh by dx is greater than 0, which means that dh by dx is positive, that is the slope of the free water surface is positive, means depth of the water increases in the direction of flow. It is increasing in the direction of flow, and there are different types of profiles obtained. Okay, we'll be dealing with the different types of profiles in the coming classes in detail. So as of now, please note this down, that is the profile of water so obtained is known as the backwater curve. Okay, we are getting a backwater curve. There is the depth of water is increasing, and the next case is dh by dx is less than 0, or dh by dh is negative. In that case, we can see that the depth of water decreases in the direction of flow. Along the direction of flow, the depth of water is getting decreased. Like in this case, the depth of water is getting decreased along the depth of flow. Okay, dh by dx is less than 0. In this case, the profile of water so obtained is called the drop down curve. It's known as a drop down curve. Okay. About these profiles, we'll be discussing in detail in the next class. As of now, please note this down. So if they are asking for the derivation of the gradually varied flow, you'll have to draw this figure, mark all this, and then you have to explain the total energy line. You have to differentiate it with respect to x, that is so as to get the slope of the energy line and the slope of the channel bottom. Okay, and express everything in terms of the slopes and the Froude's number. We'll get the equation for the gradually varied flow, and it is important to note these cases also. Okay.